Today we're going to do some hands-on examples of how to solve some basic equations. And just as a reminder, I want you guys to recall that equations are the same thing kind of as a balance beam. The equal sign in the middle of your equation, of course this is a very, very basic one, but the equal sign in the middle of your equation is kind of like the middle of a balance beam. And it states that everything on one side of the balance beam is the same as everything on the other side of the balance beam. So in this case, x weighs as much as 6. If I put x on one side and a 6 on the other, they are going to be balanced out because x is equal to 6. You guys will also recall from when you've used balance beams in the past, I'm sure, that if you do something like let's say we're nice and balanced right now, x is equal to 6. Let's say I add a little something over there. It's totally thrown my balance beam out of whack because I just made this side heavier than this side. X weighs 6, so without the extra one, it's totally balanced out. But as soon as I add this extra one, it's made the left side heavier. So now I've got to do the same thing over here. So once again, it's balanced. You hear in class sometimes that what you do to one side of the equation, you have to do to the other. That is so that you can keep it balanced. So if I get rid of this extra one, all of a sudden I'm out of balance again, but I can fix that by getting rid of this extra one. Sometimes, actually more often than not, in math class you're given an equation where it's not just a simple basic one like this where you get to see how much the variable balances. Instead, you have to do a little maneuvering to get the variable all by itself. In this particular equation, again, this is a very simple one. We're just using it kind of as an example. So if I put an x on one side of my balance beam, and then 7, 2, 3, 4, 5, 6, and 7. This is everything that is on the left-hand side of my equal sign. Remember that the equal sign is kind of right here in the middle of your balance beam. If I put a 3, now I'm nice and balanced out. My problem, though, is that I can't figure out exactly how much the x by itself weighs because I've got all of these other little ones here with it. So I need to get that variable by itself. The word for getting that variable by itself is called isolating the variable. In real life, when you've heard the word isolate before, it refers to when somebody is by his or herself. That person is isolated. In those prison movies, sometimes you hear about them sending a guy to isolation because he got into a fight. That means he's by himself and he's not with all the other people. So in order to be able to isolate this variable, I'm going to take my 7 and I'm going to just get rid of them. So I'm going to toss them off here. 1, 2, 3, 4, 5, 6, and 7 were just taken away. But of course, because I took that 7 off of the left side of my balance beam, now it's out of balance. So I need to take 7 away from this side to balance it out. The problem, though, is that I don't have 7 to take away. So hopefully we remember from when we did our study of integers that instead of taking away 7 like I did over here, I can add a -7 to this side of my balance beam because adding a negative is the same thing as subtracting a positive. So I'm going to add 7 negatives. 2, 3, 4, 5, 6, and 7. And voila! It's nice and balanced. Hopefully you'll recall from our study of integers last year and some this year that what's really going on here is that these 3 positives are canceling out 3 of these negatives. So they're really just kind of gone. A positive and a negative cancel each other out. So that means, whoops, my pen's kind of acting a little bit funny here. So these 3 negatives are canceled out with those 3 positives. So all I have left over is 4 negatives. So that means that x balances out with a -4. So remember, getting that x by itself and seeing how much it balances with is called isolating the variable. That's going to be very important in just a bit. Today, instead of using a balance beam, however, you guys are going to use something called algebra tiles, and it's something that you should have at your desks. And they're little tiles that look like this. Let me get this out of the way for just 1 second. So the blue strip, instead of the balloons and the little boxes like we had for our example in our previous example, now we're just going to use the blue strips represent an X. The red strips that are the same size as the blue strips represent a negative X. The green represents a positive 1. And the little tiny reds that are the same size as the green represent a negative 1. You guys are also going to be using a balance beam, but we'll talk about that in just a little bit. Right now, let's make sure that we know how to make a model with these manipulatives. So if I were going to ask you to make a model of an x plus 3, take a minute, try to activate your background knowledge. I know you've done similar things like this before. Try to use the tiles that you have to make a model of what x plus 3 looks like. Pause the video, try to make your own model now, and then restart the video once you think that you have that model made. I am going to go ahead, however, and work it. Make my own model, so x plus 3. Right here, I've made a model because this is my x, and then this is a positive 3. So I've got my x is represented by my blue. This is my x, and then my plus 3 is represented by 1, 2, 3 of the little units. So 1 blue and 3 green represent a model of x plus 3. Let's take a look at another example. You guys pause the video in just a moment. Try to make your own model of an x minus 3. Then check yourself with my work in just a moment. So pause now. Try to make the model of x minus 3. If you made your model of x minus 3 correctly, you should have something that looks like this. You should have a positive x, and then you should have 3 negative units, because each of these represents a negative 1, a negative 2, a negative 3. So this would be a model of x minus 3. Now try to make a model of 3x. What would a model of 3x look like? Pause the video, try to make it yourself, then go back and restart the video to check your answer. If you made a model of 3x correctly, it should have looked like this. You should have 1, 2, 3 x's, because it means you've got an x and that you multiply it by 3. A lot of people get confused and think that this represents, so remember, I'm getting ready to show you the wrong thing. A lot of people think that this means 3x, where you have 3 units next to an x, because that's what it looks like in the algebra, right? You've got a 3 sitting next to an x. But this is actually a model of x plus 3, because you've got an x plus, you've got 3 more. A model of 3 times x is just like I just said. You've got your x right here, and you multiply it by 3, so that you got 1, 2, 3 x's. You guys are also going to, now that we've gotten a little bit of practice with using them, now grab your handout that looks like this. It looks like this is kind of our generic version of a balance beam. And you guessed it, just like our examples that we have right here on our balance beam, our equal sign is right here in the middle. Just like I've got an equal sign right here in the middle of my balance beam. Everything that goes on the left-hand side of the equal sign is going to go over here. Everything that goes on the right side of the equal sign is going to go over here. So you guys are going to actually build some models now of some equations. And I'd like you to start with a model. Oh, I'm sorry. Whoops, I take that back. We're going to make one more model of an expression before we continue with equations. Totally forgot. Now this one's a little bit tough. It's tricky. So you made a model previously of 3x by making 3 of the x's. Now, what about a model of x divided by 3? Pause the video, take a moment to try and figure that out on your own, and then restart the video when you think you got it. And again, this one's hard. It's okay if you're not positive about your answer. So now let me show you. I'm assuming that you've paused the video. You might have had some discussion with your group. So I am going to make a model of x divided by 3. Remember that fraction bar is another way of saying divided by. So this is my whole number x right here. Hopefully everybody, well, it's not a number, my variable x. Hopefully everybody agrees with me. So an x divided in 3 pieces would look like this. This would be an x divided by 3 because it's an x cut into 3 separate pieces. So a model of x divided by 3 would look like this because it's 1/3 of a whole x. It's like you took that x and you chopped it into 3 pieces, and this is one of them. So this would be a model of x divided by 3. You'll notice that in your little set of manipulatives, you guys actually have some pieces that look like this, where they are cut along the lines right here. So you can actually, you're given scissors. So if I ask you to make a model of x divided by 3, you would take one of these x's that's already split up for you, and you would cut it into, you'd cut off 1/3, and this would be a model of x divided by 3. While we're at it, how about we do a model of another example, just to make sure that it makes sense to us. How about we make a model of, let me get rid of all this extra junk here. Get all this out of the way, just to make sure we understand. Let's make a model of x divided by 2. So this is what a whole x would look like. So what would an x divided by 2 look like? Pause the video. See, look at what you got in front of you as far as your algebra tiles go. So this is a whole number x. What would an x divided by 2 look like? Pause the video, try to figure it out. I'm going to assume that you have an answer, so let's check it. I'm going to pull out of my basket. This is still a whole x because it's the same size and the same color as this x. But now I am going to take my scissors and I'm going to slice it in half. So I'm going to pull out, oh, oops. Don't want to do that. Well, I kind of rotated them around, but that's okay. Okay, so I'm going to cut it apart. So now here's one. There's half of an x. I'm going to take the other half, put it over here to the side for right now. So I took this x and I cut it in half. So x divided by 2 would be a whole x divided into 2 pieces, and that would be half of it. So x divided by 2, a model would be half of an x. So now that we've gotten some practice with modeling, now let's go ahead and try to build some equations. And like I said before, this is going to be you're going to use your balance beam. And on one side of your balance beam, you've got whatever is on the left side of your equal sign. So everything to the left side of your equal sign goes over here. You got your equal sign in the middle. Everything on the right side of your equation is going to go on this side. So I want you guys to try to build a model of 2x minus, and actually, I goofed. This should be a 2x minus 7. So pause the video for a moment, look at your algebra tiles, look at your little balance beam, try to build a model of what 2x minus 7 is equal to 5 would look like. I'm going to assume that you're pausing the video now and that you've restarted the video. And I have made myself a model of 2x minus 7 is equal to 5. Because what I did is I took 2 x's, then I took 7 negative 1's, put it on the left side of my balance beam. My equal sign goes right here, and then my 5 goes on the right side of my balance beam to make a positive 5. So your equal sign's right there in the middle. Your negative 7 is over here. Your positive 5 is over here. So that's what your model should look like. Now, I want to solve this equation. Remember that when you're solving an equation, you're trying to figure out what does x have to equal in order to make this whole equation true. In other words, you want to get it to the point that you've got just an x on one side of your balance beam and a number on the other side of your balance beam so that you can see how much the x balances out. Sometimes, like in the example we did here, you had to do a little bit of work. In the example that we did previously, this x did have 7 with it, so we had to isolate it by getting rid of those 7. That is exactly what we need to do here. So I've built my model of 2x minus 7 is equal to 5. What you should be doing right now is as you are making the model of this, you should, as we're solving it, you should also be doing this part right here on paper. So please make sure that you have on a piece of paper now 2x minus 7 is equal to 5. And then as we're taking steps to solve this problem, you should be writing down the steps. So right now, remember that my goal is that I want to isolate my variable. That means I want to get it so that it's all by itself so I can see how much it balances out with, just like the example I had here. If x balances out with a 6, so I know that x is equal to 6. So I got to get rid of all this extra junk right now. The easiest thing to get rid of, and the way that you need to do it, is to get rid of this 7. And remember that a minus 7 and a negative 7 really mean the same thing. So I'm going to take these 7's, and I'm just going to pull them off my balance beam. Just like so. I'm going to get rid of them. Oops, didn't mean to do that. So I'm pulling my negative 7 off of my balance beam. Pulling it off over here to the side. Now my problem right now is that, and hopefully you just removed your 7 as well. So what that would look like on paper also is if what I just did is I took away a negative 7. What happens when you take away a negative? Minus a minus is really the same thing as adding a 7. So that's what this would look like on paper. I had a negative 7. I canceled it out by taking away a negative. Let me say that one more time. So what I actually did is I subtracted a negative 7. I took away a negative. We remember from our integer rules, when you subtract a negative, what you're really doing is adding a positive. So that minus 7 and that plus 7 cancel each other out so that now they're gone. All I have left are the 2 x's that are over here on the left side of my balance beam. However, I've got a problem right now. So I added 7 to the left-hand side of my equation. Let me clean this up just a little bit. So I added 7, which means that all I have left are those 2 x's. My problem, as we illustrated in this example a while back, if I add something to one side of my balance beam when it's balanced, I'm going to mess stuff up unless I do the same thing to the other side. So if I add 1 over here, I got to add 1 over here. So let me go back to my example. I added 7 to the left-hand side of my balance beam, which means I need to add 7 to the right side of my balance beam. So I'm going to drag 7 more right over here. You should be doing the same thing. Six and 7. So after I get done adding those extra 7, I've got a total, if I were to count what I've got over here, I've got a total of 12 positives. So now I've got 2 x's are equal to 12. That x is still not isolated. I don't care how much 2 x's weigh. I want to know how much just 1 x weighs. So what I'm going to do now is I'm going to take these 2 x's and I'm going to divide them into 2 groups. So here's one group of my x, here's another group of x. So I just took my x's again and I divided them into 2 groups. So I divided them by 2. On paper, this is what it would look like. I had 2 x's, I divided them into 2 groups. So how much do I have in each group? Group number 1 has an x, group number 2 has an x. So 2 x's divided by 2 is just 1 x in each group. However, it's a balance beam. If I split up this side of the equation into 2 separate pieces, so if I took those 2 x's and divided them into 2 groups to get 1 x, I got to do the same thing over here to this side of my balance beam. So I got to take that 12 and divide it into 2 groups. So I'm going to do that now. So I got 1, 2, 3, 4, 5, and 6. Whoops. That didn't want to cooperate, did it? And 6. So then I got 1, 2, 3, 4, 5, and 6. So if I divide those 12 into 2 separate groups, group number 1 has 6 in it, group number 2 has 6 in it. So 12 divided by 2 is a 6. That means that 1x is equal to 6. So all of that stuff we've talked about, inverse operations, let's make sure we remember what we're talking about when we do that. Inverse operations is a fancy word for reverse, hopefully, or for opposite. So to get rid of that minus 7, I added a 7. I added a 7 over here, which means I had to add a 7 over there. So the opposite of a minus 7 is a plus 7. Then for my next step, in order to get rid of this 2 times x, the opposite of multiplying by 2 is to divide by 2. So that's why 2x's divided by 2 got me just 1x. I divided this side by 2, so I had to divide that side by 2, so x was equal to 6. Remember that word that we have used in the past, inverse operations? Inverse is a fancy word for reverse. So I had subtraction, so I added 7 to each side because adding is the opposite of subtraction. I did have multiplication, so I did the opposite or the inverse of multiplication, which is division. So the fancy word for opposite is inverse operations. So this gives you a basic introduction to using the balance beam to model. Now watch video part 2. Has the same title except it just says part 2. It's in the same folder, and try a few more practice problems using a balance beam and using your algebra tiles.